In this video, we'll have a closer look at arithmetic sequences and series. An arithmetic sequence is a sequence with a constant difference between any consecutive terms. For example, 5, 10, 15, 20, the consecutive terms increase by 5. Or another example, 7, 9, 11, 13, well, this time our terms increase by 2. The increment between consecutive terms is constantly 2. Generally, if we name the constant difference, also referred to as the common difference, between the consecutive terms an plus 1 and an by a letter d, then the arithmetic sequence has the following form. Suppose the first term is called a1, therefore the next term, a2, comes from a1 by adding this common difference, right? And the following term, a3, comes from the previous term by adding another common difference. So overall, we have a1, the first term, plus 2 differences. And the following term is whatever we had before plus another difference. So altogether, we have a1 plus 3 differences, and so on. Therefore, the nth term turns out to be a1, the first term, plus n minus 1 of those common differences. Why n minus 1? Well, when we observe the coefficient by d and the index of the term, this coefficient is 1 lower than the index. So yes, the nth term comes from adding n minus 1 of the common differences to the first term. Okay, so we've just developed the formula that allows us to find the nth term of an arithmetic sequence, knowing its first term a1 and the common difference d. Let's experience how this works using this example. An arithmetic sequence an starts with 3 and has the common difference 4. Write the first 5 terms of this sequence. Well, we know the first term, that's 3. Okay, so we have 3. And then the next term is whatever we had before plus the common difference, which is 4. So 3 plus 4 is 7, plus another 4 is 11, and plus another 4, 15, one more time plus 4, 19. Here we go. Those are the first 5 terms of our arithmetic sequence. Can we go a little bit farther and find the nth term? Yes, we can follow this formula. The nth term would be the first term, which is 3, plus n minus 1 of common differences times 4. That's our nth term, an. Okay, let's see another question. Find the 51st term of the above sequence. Well, since we already have the general formula for the nth term, it is easy to find the 51st term. Our n becomes 51. So we have 3 plus 51 minus 1 is just 50. One lower number than the index, right? Times the common difference. Altogether 203. So the 51st term of this sequence equals 203. Let's practice finding the general term of a given arithmetic sequence. In the first example, we have given the first term and the common difference. So it's enough to use this information, plug into the formula, and we'll have the nth term. An equals a1, which is 10, plus n minus 1 times the common difference, which is negative 2. And then we can simplify this expression. That becomes 10 minus 2n and plus 2. Okay, now we can add the 3 terms and we end up with 12 minus 2n. That's a formula for the nth term. Let's do the same in the second example. We see a1 because it's our first term, right? What's our d? What's the common difference? Well, if we take the second term and subtract the first, 3/4 minus 1/4 is 2/4, which is 1/2, right? Okay, so that's our candidate. Let's check if those differences are the same between other consecutive terms. 5/4 minus 3/4 is still 2/4, so yes, it confirms. And 7/4 minus 5/4 is 2/4 again. So yes, that's the common difference. This is indeed an arithmetic sequence. Therefore, we can calculate the nth term using this formula. A1 is 1/4 plus n minus 1 times d, which is 1/2. Okay, so we have 1/4 plus 1/2 of n and minus 1/2. Okay, that gives us 1/4 minus 1/2. It's negative 1/4. So altogether negative 1/4 plus 1/2 n. That's the formula for the nth term. Now let's find the 25th term of the following arithmetic sequences. To do that, we could use directly the formula for A25, or we might as well find the general formula for an first, and then replace n by 25. In both instances, we need to know a1 and d. a1 is already given. It's negative 14. What about d? What's the common difference of this sequence? Well, let's take one of the term and subtract the previous one. So it's negative 11 minus negative 14. That gives us negative 11 plus 14. Oh, that's 3. Okay, so an equals the first term, negative 14, plus n minus 1 times the common difference 3. That gives us negative 14 plus 3n and minus 3. Altogether, negative 17 plus 3n. So that's our general formula. And now we can calculate A25. So it is negative 17 plus 3 times 25. Okay, so we have negative 17 plus 75. That gives us 58. The 25th term of this sequence is 58. One more example. This time we have given the 11th term and the 17th term. We don't know a1 and we don't know d. So we'll look for two unknowns. Therefore, we'll need to develop two equations and then solve the system of equations for these two variables, right? The first equation comes from this information. Since we know that a11 is 6, let's express a11 in terms of a1 and d. Well, a11 would be a1 plus 11 minus 1, so it's 10 times the common difference d, and that's equals 6. In the second equation, we can state a17 in terms of a1 and d. That's a1 plus 17 minus 1 is 16d equals 15. Okay, so we have the system of these two equations with two variables. So we know how to solve it. We can, for example, subtract the top equation from the bottom equation side by side. That will eliminate a1, right? So a1 minus a1 disappears, and then 16d minus 10d is 6d. On the other side, 15 minus 6 is 9. Therefore, d by itself is 9 sixths, which can be reduced to 3/2. That's our common difference. Okay, let's come back to one of the equations. For example, the first one, to find a1. a1 equals 6 minus 10d. 6 minus 10, and instead of d we have 3/2. Right? So that will be 6 minus, when we reduce the 10 with 2 we get 5 here. So 5 times 3 is 15. Altogether negative 9. Our a1 is negative 9. Okay, so now we can figure out what's a25. That's first term, which is negative 9, plus 25 minus 1 is 24 times the common difference, which is 3/2, equals, and let's simplify the 24 with 2. That gives us 12 in the numerator, so we all together have negative 9 plus 3 times 12, which is 36. That equals to 27. So the 25th term of this sequence is 27. A slightly different type of question. Find the number of terms in each arithmetic sequence. We have given first couple terms. That allows us to figure out what's the common difference d. 5 minus 9 is negative 4. 1 minus 5 is negative 4. So negative 4, that's our common difference. And the first term, a1, is indicated here. It's 9. Since this is our nth term, an, using the formula for the nth term, we have a1, which is 9, plus n minus 1 times the common difference, which is negative 4. This nth term is equal to negative 35. So we set up an equation with one variable n. And this n really represents the number of terms, because that was the nth term, right? So we just need to solve this equation for n. Okay, first let's subtract 9 from both sides of the equation. We'll have n minus 1 times negative 4 equals negative 35 minus 9, it's negative 44. And then we can divide both sides by negative 4 to reduce it, leaving us with n minus 1 equal to 11. Therefore, n by itself is equal to 12. There's 12 terms in this sequence. Okay, let's look at the second sequence. Again, we have a1, which is 3/5. And what's the common difference? Well, it's 11/10 minus the previous term, which is 3/5. 3/5 is the same as 6/10, right? So 11 minus 6, that's 5/10, which is the same as 1/2. Okay, we have the common difference. And now, as before, we can set up the equation that will compare the formula for the nth term with the value of this term. Okay, the nth term is the first term, 3/5, plus n minus 1 times the common difference, 1/2. And that's equal to 31/10. Now it's enough to solve for n to answer this question. Okay, as before, let's subtract 3/5, which is 6/10, from both sides. That leaves us with n minus 1 times 1/2 equal to 31 minus 6 is 25/10, which could be simplified to 5/2. Okay, in the meantime, we're going to multiply the whole equation by 2 to get rid of this 1/2, right? So we end up with n minus 1 on this side equals 25/10, that's 5/2, but we are multiplying by 2, so these two will be cancelled. Okay, therefore we have n minus 1 equals 5, which leads us to n equals 5 plus 1 is 6. There's 6 terms in this sequence. Now let's see how to find the partial sum Sn, the sum of the first n terms of an arithmetic sequence. Well, let's write our partial sum Sn in the form a1 plus a2, which is a1 plus d, plus a3, and so on until an. This is our an, right? That's a2, that's a3, and so on. And now let's write the same sum, but starting from the nth term and going down till the first term. So if we write an in the first place, the an minus 1 is the same as an minus the common difference, because the consecutive terms differ by d, right? So if we go to the consecutive term, but one lower, one before, it will be minus 2d, and then minus 3d, and finally an minus n minus 1 of these. This last term is actually the same as a1. Please convince yourself that this is true. It's enough to replace an by the formula for nth term, and then this whole second term will cancel, leaving us with a1. After lining up the consecutive terms of the two sums, let's add the two equations side by side. So on the left-hand side, we obtain 2 of those sums. Let's see what's going on the right-hand side. Observe that each column adds up to a1 plus an. In this column, the d will cancel each other, right? So it's again a1 plus an. In the next column, the two d's will cancel, so we have a1 plus an, and the last column as well. This expression will cancel, so we have a1 plus an. Okay, so it's a1 plus an, and in the second column we have a1 plus an, and in the next column the same, and in all those columns we'll end up with a1 plus an. Therefore, we can rewrite this equation as 2sn equals how many of those columns? Well, there are n of them, because we are going from a1 to an. Therefore, this equation becomes a1 plus an taken n times. So, this calculation leads us to the equation Sn, the sum of the first n terms of an arithmetic sequence, equals, we just divide by 2 on the other side, right? a1 plus an over 2 times n. We can see this as the average of the first and last terms taken n times. Okay, so we developed a formula for calculating partial sums of an arithmetic sequence. The most commonly used form of this formula is this one or that one. However, sometimes we may want to use an equivalent formula like this. This second formula comes directly from the first one after substituting the expression a1 plus n minus 1 times d in place of an. You may want to pause the video, perform this substitution, and convince yourself that these two formulas are indeed equivalent. Let's see how to use the partial sum formula. Find the S10 for each arithmetic sequence. What S10 means? As you remember, that's the sum of first 10 terms of the given sequence. In the first example, we know the first term and the common difference. We don't know the 10th term. So in order to use this formula, first we should come up with the value for a10, right? But we know that formula. This is the first term, which is 8, plus 10 minus 1, which is 9, times the common difference, which is 5. So altogether we have 45 plus 8, that's 53. And now we are ready to use the formula for S10. S10 equals 1/2 times 10, 10 terms, first term, which is 8, plus the last term, the 10th term, which we just calculated, it's 53. Okay, let's carry on. We can reduce the 2 with 10, so that will be altogether 5 times 53 plus 8 is 61. That becomes 305. Okay, so you see, that's pretty powerful. We don't see the terms, we have just some pieces of information, and we can still come up with the sum of the first 10 terms of the arithmetic sequence without even seeing it. Let's go on to the second example. Now the nth term is given as a formula, so it's easy to come up with the first term, which will be needed for our formula, right? So a1 is when n is 1. 1 times 4 plus 3, that's 7. What else do we need? Since we are calculating S10, we need A10, right? Therefore, let n be 10. We end up with 3 plus 4 times 10, 43. Okay, now we are ready to find S10. That's 1/2 times the number of terms, which is 10, times the first term plus the last term, so 7 plus 43. That becomes 1/2 times 10 is 5 times 50. 250. 250. And we're done. Happy face. Now let's recall how to evaluate sums written in sigma notation. Okay, let's analyze what do we have here. We are really summarizing all consecutive numbers from 1 to 100, because the expression indicating terms to summarize is just I. Notice that this could be considered as the sum of the first 100 terms of an arithmetic sequence with a1 equal 1 and the common difference equal 1 as well. So this is really the same as S100 in our previous notation, isn't it? Therefore, according to our formula, this is equal to 1/2 times 100 terms and times the sum of the first and last term, so 1 plus 100, which is 101. Okay, so that's really the same as 1/2 times 100 is 50 times 101. Altogether 505 and extra 0, so 5050. Now let's add numbers from 1 to n, since this is really the same as Sn, right? And again, our first term is 1 and our common difference is 1 as well. We're using the terms of the same sequence, right? Consecutive numbers. So the formula would go 1/2 times the number of terms, but the number of terms is n this time, times the sum of the first and the last term. What's the first term? Well, it's 1. What's the last term? Oh, it's n. Notice that our formula could be written in a form n times n plus 1 over 2, or 1/2 times n plus 1. So if we summarize consecutive numbers from 1 to n, we multiply the last number times the next number, and we're taking half of this product. Observe that in our previous case, we indeed multiplied the last number by the next consecutive number, and everything over 2. This formula will be used quite often, so it's a good idea to memorize it. N times n plus 1 over 2. Let's see how to calculate the sum of constant terms k from 1 to a certain number, in this case 250. Since k does not depend on the index I, we have k for the first term, and the second term is still k, and the third term is k, and so on until 50th term, which is also k. So we really have 50 times the same term k. So that's the same as 50k. Okay? So if we have a constant number under this big sigma, the value of such sum is k times the number of terms, which in this case is 50. One more example. This time the terms have form k times I, where k is a constant and I is our summation index, which changes from 1 to 50. So what this really means? Well, we have k times 1 for the first term. When I is 2, we have k times 2. When I is 3, we have k times 3, and so on until we get k times 50. So now we can factor out the constant k. Therefore, we have k times 1 plus 2 plus 3 plus until 50. Okay, and now we can apply a formula for the sum of the first consecutive 50 numbers and multiply it by k. That's k times, and now it's 1/2 of the number of terms, which is 50, and then sum of the first and last term, which is 51, right? If we reduce the 2 with 50, we end up with 1275 for this product times k. That's the overall sum. Notice that anytime we have a constant factor under the sigma sign, we can pull it out of the whole sum. So this sum could be actually written k times the sigma of I, where I changes from 1 to 50. This whole sigma from 1 to 50 is over there, right? So we develop a few rules already. The sigma of i's from 1 to n is equal n times n plus 1 over 2, and the constant k can be pulled out of the sigma notation. Let's keep this in mind. The next example seems to be a bit bigger. Before we start evaluating this particular sum, notice one more property of the sigma notation. Suppose we have a sum of expressions ai plus bi, for I changing from 1 to a certain number n. Because of commutativity of addition, we could rewrite this sum by summarizing all ai terms first under the sigma of ai, and then summarizing all bi terms under the sigma of bi, for I from 1 to n in both cases. How do we know that that's true? Well, if we rewrite what this sigma stands for, we'll get a1 plus b1, that's first term, plus a2 plus b2, second term, and so on until the last term, an plus bn. But because of commutativity of addition, we can rewrite the sum as a1 plus a2 add all those A entries first, plus AN, and then add all those B entries, B1 plus B2 plus Bn, right? So we started with this sum, and we ended up with the sum of A's plus sum of B's, right? That tells us that the sigma sign can be split over addition. And obviously similar justification would work for subtraction as well. You may want to check on that. Okay, let's keep this in mind. This rule will make it easier to calculate sums like this. We could split the sigma sign to these two terms. So we can rewrite this as sigma of 2i's from I equals 1 to 70 plus sigma of just constant 3 from I equals 1 to 70. Now, in the first sum, we have constant times I. So using the example from the last slide, we know that we can pull this constant number out of the sigma sign. So that's the same as 2 times the sum of i's, where I changes from 1 to 70. And then it's plus sigma of 3, constant number 3, from I equals 1 to 70. And we already know how to calculate this sum, isn't it? Okay, so we have 2 times the sum of consecutive numbers from 1 to 70. That's 1/2 times the last number 70 times the next number 71. Plus sum of constant numbers 3. How many of them? 70. So it's 70 times 3. And that's all. What's left is just to perform this multiplication. So the 2 is cancelled. 70 times 71 is 4,970, plus 3 times 70 is 210, which altogether gives us 5,180. One more example. This time I will ask you to stop the video and try to evaluate the sum on your own. Let's see it. Again, we can distribute the sigma sign to each term. So it's sum of 1/2 I from I equals 1 to 20 minus sum of 1s from I equals 1 to 20. Okay, so we can pull the constant 1/2 out of the sigma sign and then summarize the consecutive numbers from 1 to 20. Minus, this can be already replaced by how many terms? 20. What kind of terms? 1. So 20 times 1. Here we go. 1/2, the sum of the consecutive numbers from 1 to 20 is 1/2 of the last number times the next number, 20 times 21, and minus this 20. That becomes, we can reduce these 2's with 20, so 20 divided by 4 is 5, and 5 times 21 is 105, minus 20. So the overall value is 85. Here we go. Finally, let's look at one application problem. There are 20 rows in a theater. The first row has 28 seats. The second has 32 seats. The third has 36 seats, and so on. How many seats are there in the last row? How many seats are there in the whole theater? Well, we can look at the number of seats in each row as terms of a certain sequence. So the first row has 28 seats. Let's record this as A1 equal 28. The second row, A2, is 32 seats. The third row is 36 seats, and so on until the A20, because there are 20 rows there, right? What the question asks for is how many seats are there in the last row. So what we need to find is A20. And the next question asks us how many seats are there in the whole theater. That means we need to add all those seats from all rows, which really means we are after S20, isn't it? The sum of the first 20 entries in our sequence. Now, we know how to calculate A20 and S20 if we work with an arithmetic sequence. Is this an arithmetic sequence? Well, let's check. 32 minus 28 is 4, so the common difference would be 4. That's our candidate. Does it work for the next pair of terms? 36 minus 32, it's 4. So yes, we have confirmed this is arithmetic sequence. We can use formulas for A20 and S20. A20 is A1, which is 28, plus the 20 minus 1, which is 19, times the common difference 4. So that gives us 104. The 20th term is 104. So that means we have 104 seats in the last row. Okay, we have answered for the first question. What about the second question? How many seats are there in the whole theater? Well, we need to add seats in all rows. That means calculate S20. S20 is 1/2 times the number of rows, which is 20, and then add the seats from the first row and from the last row. Here we go. That gives us, reduce the 2, 10 times 132. So it is 1,320 seats in the whole theater. There are 1,320 seats in the whole theater.